Thank you very much for the introduction. I would like to thank all of the program organizers and the workshop organizers for inviting me here to give me the opportunity to present some of our recent work. And I'm really glad to come back to IPAM, where I have been participating in a number of workshops and programs. It's always, please keep inviting me. OK, so what I'm going to talk about is mathematical analysis. In particular, I'm going to demonstrate a number of PDE analysis, to be specific. It's not arbitrary analysis. And then what I'm going to focus on is analyzing different kinds of quantum algorithms, like how do mathematical analysis tell us in terms of better understanding quantum algorithms. So for those who are not quantum computing experts, quantum algorithm just means algorithm that runs on quantum computers. And that's what I'm going to talk about. So a little bit of outline of what I'm going to discuss today. So at the very beginning, I'm going to give some motivations of quantum computing, or generally, what do people care about when people work on quantum computing. I'm a mathematician working on the theory of quantum computing, and that's what I do for most of the time. And specifically, there are two types of dynamic simulation problem that I'm going to address. The first one is related with the closed quantum system. So it's not, you will not explicitly see the density matrix floating around all the time because I'm working with the pure state, but you can formally, translate that into your familiar language. So the first topic I'm talking about is going to be closed quantum system Hamiltonian simulation. I will define the problem. The second topic I'm going to talk about is open quantum systems, specifically Lindblad equation, where you will see density matrix floating around. Just as a head up, for the first part, the analysis I'm going to use are semiclassical microlocal analysis. I know there are experts in the audience. And the second part, I will mention hypocoercivity, which corresponds to Francois' previous question in the morning. Hopefully, you will like this part. All right, so at the very beginning, I'm going to address the motivations and maybe the big elephant in the room. Do quantum computers exist? The answer is certainly yes, the quantum computer do exist, as has been summarized in this figure. This particular slide was contributed by my friend who is an experimentalist. It's a little bit outdated because Google already have a much robust and better quantum processor, but this sort of gave you an idea how quantum computer looks like and what are the corresponding hardware technologies for various different quantum computers. So as you can see, the quantum computers comes in different type and shapes. So the physics is also very different. When you look at all of these figures, you might think that then, well, many industry are really pulling big money and they are trying to construct very great, good, robust quantum computers. What about academia? Say in universities, is there any university that has a large, good quantum computers in place at the university level? I think we are fairly proud that Duke Quantum Center, that's where I'm sitting in, and we are leading this trapped ion technology. But certainly, this talk is a mathematical talk. I'm not going to dive into all different kinds of machine, how the physics underlying is going to work. So first of all, let me just say a little bit, this is one of the superconducting quantum computer that I take a picture last year. And this is our out of the 6 Duke quantum computers, this is one of them. And when you open there, you can see they look completely different. But as a simplification for the talk today, we're mathematicians. Many of us are mathematicians. So I'm going to do this oversimplification, which is sufficient as an intuition and for the purpose of this talk. I'm going to say that let's imagine quantum computer as this computational device that operates on this matrix vector multiplication problem super fast. You may wonder, you can ask me, like, D, how fast is super fast? Imagine I have a problem of dimension n. Let's imagine we gave it to our undergraduate student who is taking a linear algebra course with us, say, OK, let's compute. Probably they will see of order n squared, right? You just compute everything by hand. Let's think about what is the last century most celebrated classical algorithm. I think if you agree with me, it's arguably fast Fourier transform, FFT. What FFT is able to do is essentially stating that given certain structures of the matrix A, instead of n squared, we can get it down to n log n, from quadratic to almost linear, and that's significant. Now you may wonder, what does quantum bring on the table? What is the potential power that quantum computers can give? This is what we can get. It's not giving you, linear in n, quadratic in n, things like that. There is a potential. It's not always the case, but there is a potential we can get away with only log n, polylog n, where this is the potential exponential power. That's why people are all excited about this field of quantum computing in general. Enough about the motivation, but now I want to discuss a little bit more on this crucial term, so-called exponential quantum advantage. Mathematically, actually, this is a super polynomial quantum advantage instead of really a true exponential. You will see very soon. So then you may wonder, like, there are various different kinds of computation problems. You can choose your favorite computational problem, simulated differential equation, optimization, machine learning. Well, whether they have any speed up, I'm not going to discuss about that. But the point is, you can, for any well-defined computation problem, if you want to claim that for this computation problem, I have a quantum advantage, what should you do? Mathematically speaking, we are mathematicians, we prove theorem, is that we need to prove at least 2 theorems. One is that we need to show this problem is quantumly easy. The other is that we need to show this problem is classically hard. Specifically, for any given computational problems, let's imagine, suppose there are n parameters in the problem, and then you need to construct a quantum algorithm where you need to show as a theorem that the quantum complexity, the gate complexity, namely how many operations you need to calculate this computational problem, is upper bounded by polylog n. This is efficiency for quantum side. And at the same time, you also need to show this problem cannot be efficiently simulated classical side. So what do we need? What are the theorems to prove? So there are 2 criteria I believe is widely accepted in the community. The first thing is that suppose your computation problem is really well studied, say by many people in different fields for decades and decades. One example is the integer factoring. Then for that particular well-studied problem, people will trust the best known classical algorithm result. This best known, by the way, also includes all of the deterministic algorithm as well as the probabilistic algorithm. Just comparing a specific class is not sufficient. You need to look at them all. So for a well-known problem, you look at the best known result, and you want to show that classically you cannot do polylog n. Instead, you have something that is exponential. The reason we call it it's really a super polynomial speedup is because they may not have the same polynomial. By the way, throughout my talk, when I say polynomial, I do not necessarily mean the power has to be an integer. N to the 1/3, I also call it a polynomial for this case. You can imagine that for many of the computation problem, maybe it's fairly new. It just got into interest in the past decade, or someone proposed it. Maybe it hasn't. It's an old problem, but maybe it hasn't been studied by many people in many fields for many decades. Then what do you do instead? So in that case, there is also acceptable criteria where if you can prove your problem is actually BQP hard. This is a complexity class, which I'm not going to dive into the details, but the point is that if that's what you can show, the unreasonable complexity conjectures, particularly BQP does not equal to BPP, then people believe that there should not be any classical algorithm, whether they exist or does not exist, that none of the classical algorithms should give you polylog cost. So this is sort of the criteria of the exponential separation. Now we know the criteria, the next natural question are there, then what are the computational problems that we already know that are giving us a quantum advantage? Well, I would like to recommend a very nice web page hosted by Stephen Jordan, currently at Google Quantum AI team. The web page is called Quantum Algorithm Zoo, where you can search the web page. There will give you a list of hundreds of applications and what are the separation. Is there any separation? Is the separation polynomial, quadratic, super polynomial, or exponential? But for today, just as a little bit of teaser, I will just say, in my opinion, I really like these 3 particular applications. The first one is a very famous example, integers factoring, goes back to Peter Shor. That's who needs no introduction. And then the second example is if we want to invert a large sparse linear system, suppose the sparsity also is polylog n, and then you can efficiently solve it by quantum linear system algorithm. A particular one is called HHL, Hasidem, Aram-Harrow, and Seth Lloyd, named after these 3 folks. And today, what I'm going to talk about is Hamiltonian simulation. So Hamiltonian simulation is that I have a closed quantum system that is governed by certain Hamiltonian. I just want to deal with the simulation. So just a little bit to say that for these, you can see the criteria is slightly different. For Hamiltonian simulation, it's satisfied the criteria B, which means it is actually a BQP hard problem. So then it just becomes we want to construct a efficient quantum algorithm. In other words, say hopefully get a polylog n, and then at least we can say theoretically there is a quantum separation. All right, so now comes to the first part of the work where this is a set of very talented graduate students. I choose to talk about this particularly because I co-organized the long program back in 2023 at IPAM in quantum computing, and this is the outcome of our working group. So I think it's very nice that these people were graduate PhD students at the time. Now they are going into postdoc positions, and we had some very nice paper coming out, and there are some interesting follow-up. So here, I'm going to define the problem, concretely Hamiltonian simulation. Actually, Hamiltonian simulation was really dated back to the 80s, where Richard Feynman proposed why, the original motivation to build a quantum computer. The story can be simply phrases as that, nature acts quantum mechanically, then why don't we make our computational device quantum mechanical as well? So hopefully they have the same degrees of freedom, we can efficiently simulate them. So concretely, on the mathematical level, I'm just going to talk about, the Schrödinger differential equation. It can be an ODE or it can be a PDE, depending on what is the Hamiltonian. So the setup is really simple. The whole dynamics Schrödinger equation is governed by a Hamiltonian that can be time dependent. Think about Laplacian plus potential or some time-controlled Laplacian plus some external field and so on and so forth. And then correspondingly, what we need for this task is that I want to construct an approximate unitary because the exact form is a unitary. Either you have the exact matrix potential or you have a time ordering to compensate, Hamiltonian at different time may not commute with each other. But the point is that we want to construct an approximate unitary that we can efficiently translate into a quantum circuit so that it can be run by a quantum device. So it's not always any formulas can be efficiently translated into a quantum device because quantumly we know there's this no cloning theorem states that you cannot efficiently generate copies. So this generates a lot of issue to create the quantum circuits and so on. But for my talk today, I'm going to mainly focus on the analysis part where I'm not going to bother you with how I construct a circuit. Just say that I can do them. And then the point is that we want to get an error threshold guarantee, particularly this is typically what people use as the typical error metric for Hamiltonian simulation, which is also actually the worst case scenario, which means that if you can show this is true, that it works for arbitrary initial condition and arbitrary observables, because those were just loser, like a weaker error metrics. And then, so basically, we want to analyze that once we can convert it into a quantum circuit, and then what is the cost, how many quantum gates particularly that I need to run this circuit. So again, the motivation of Hamiltonian simulation, besides its apparent physical and chemical applications, I also want to mention that it is actually also a very important subroutine for many of the quantum algorithms for scientific computing purposes, such as matrix inversion and quantum optimization and so on. You can imagine, classically, if we want to invert a matrix, we will never turn it into a Schrödinger equation and simulate that. But turns out it's an important subroutine for many of these applications. You have to deal with that. So that's why Hamiltonian simulation is remaining as one of the most basic fundamental and also viewed as the nearly, hopefully, achievable quantum, practical quantum advantage task. So what I want to mention is that the difficulty of the simulation problem on a very high level, you can sort of imagine, it increases as the underlying unitary become more and more highly oscillatory. You can imagine maybe there are two sources of oscillation. One source is, suppose operator norm is large, then the underlying unitary is wrapping around very fast. The faster there are, you need more cost to resolve what is properly going on. Or you can also see it by rescaling the time by the operator norm. Then you can see the longer the time, then the higher cost you need. Another oscillation is that suppose the Hamiltonian itself is time dependent, it's oscillating, and then this will also give you additional costs in order to resolve what is properly going on in the dynamics. Please, Mark.
Just one question. On the left-hand side, you have a T.
Yeah.
Do you want uniform control for all T?
We do not want for uniform control for all T. Actually, one can prove that there is a lower bounds, no fast-forwarding theorem essentially states that linear in T is what we expect to get for generic Hamiltonians. It doesn't mean that, for diagonal Hamiltonian, or there are specific we call fast-forwardable Hamiltonians where you can get a uniform in T cost, say diagonal, you can just, right? But generically, for a set of generic Hamiltonian, usually linear in T is the best one can hope for. Yeah, with a much lower bound. Very good question. Is there any other question before I move on? Please.
Could you explain that question? What do you mean by uniform control of T?
Yeah, so the cost, suppose if we want to prove a theorem, here is the quantum gate complexity. What is the dependence you expect in terms of T? So the uniform in terms of T would mean like independent of T. Then for very specific type of Hamiltonians, it is possible, say if it's diagonal Hamiltonian or diagonal in the Fourier basis and so on, those are called so-called fast-forwardable Hamiltonian. But for more general Hamiltonians, linear in T is what is expected.
T being the final time? Or
the final time, yeah, that's right.
On the left.
Yeah, sure. So now I'm just going to discuss a little bit about the state of art of the various different kinds of quantum algorithm. I would vastly say this split into two types. One type is trotterization, where it's such a celebrated algorithm dated back, has a super long history, as you can see. It's so celebrated to the level it has different name. So if we talk to physicists, it's called trotterization. Now I also like to call it trotterization. If we talk to computer scientists, usually it is called product formula. If we mathematicians sometimes call it time splitting and operator splitting, nevertheless, they actually mean the same thing. Actually, I know many of the audience, there are a number of experts audience has proved bounds for this particular problem. So here is the history, and I'm going to skip it. The point is that you can actually, this is a approximation, operator approximation. Certainly the operator norm will depend on the error will depend on certain operator norm. This L means that how many times you need to repeat what is underlying. Suppose you can imagine I can put this whole thing as a building block, I create its quantum circuits. This L tell me how many times I need to run this quantum circuit. So this corresponding to the so-called Curie complexity, and the gates per Curie will then mean like for each of the time step, what is the circuit that I need to implement for this particular simulation? So it's a trivial to just see that we should have a commutator scaling. You can easily prove it by variation of constant if you'd like using simple three-line arguments. The point is that commutator scaling is an improvement comparing to the original operator norm squared. So if your operator norm is large, namely the first oscillation, you really want to get a commutator scaling, so there's additional cancellation. As simple as that. Here I just gave a very simple demonstration saying that position plus momentum. Momentum is a differential operator from L2 to L2. That's where the wave function lives in. The operator norm is infinity. Versus if we look at the commutator, it's just as small as 1. So commutator scaling sometimes can really do you wonders. So if you have an algorithm, you may want to achieve that. There are various post-Trotter algorithms where I cannot simply just write some simplified mathematical formula to simply discuss what they are. I need several lectures and so on. So I will not do that. But the point is that all of the post-Trotter algorithms, the Curie complexity all depends on certain polynomial of the Hamiltonian itself, not a commutator. So just to recap a little bit, there are two sources of highly assertive source. We certainly want to have weak dependence on both. For example, we want to have a commutator scaling if we can, and the second, we want to have log dependence on the derivative as opposed to polynomial dependence. So a major takeaway of all of the existing algorithm is essentially that the Curie complexity, if we look at the worst case scenario or the typical error bounds, it will always rely on certain polynomial of the Hamiltonian or polynomial of maybe the operator norm. Nevertheless, there are some operator norm getting involved. However, the gates per Curie, if you really design your circuits carefully and good enough, the gates per Curie will be poly n, where n is log dimension of the original Hilbert space. So 2 to the n is capital letter n. So throughout my talk, I'm going to use capital letter n for the size of Hilbert space, and 2 to the n, little n is the number of size, the number of qubits, the number of bodies, however you like to call it, is poly n, poly little n is what I want to get. Okay, so I would say that for Hamiltonian simulation, this is a really well-studied problem. If the Hamiltonian is bounded, that from my perspective, the theoretical level, the story is complete in the sense that you already have a quantum algorithm whose upper bound matches all the parameters of the lower bound. So asymptotically speaking, at least that picture is complete. However, what I'm going to address today is what about unbounded operators? So what if Hamiltonian is unbounded? If you look at all of the Curie complexity, all of a sudden you have infinity. So it's not so clear what is going on in all of these algorithm analysis. But before that, I just want to say a little bit, why do we even care about unbounded Hamiltonian? Please.
Just regarding
sure.
In the previous slide, are there some rigorous results showing that time dependence can make the simulation harder than?
Exactly, yeah. Yeah, exactly. Time dependence will make the simulation much harder. And actually, so these are the takeaway. When I say matching the theoretical lower bounds, these are mainly meaning for time-independent Hamiltonian simulations. So for time-dependent Hamiltonian simulation, linear in T is we can get linear in T log dependence on the precision, but it's not quite an additive error bounds as opposed to time-independent case. QSVT and QSP can give us additive error bounds. But yeah, but that's a full story for another day. Thank you. Okay. So just for some motivations, maybe you have molecular dynamics where the system size is very large due to the high dimensionality, or maybe electronic structure in the first quantization. This is a picture that I took from a very popular line of research on quantum optimization and so on. And they also working with this type of Hamiltonian. In particular, all of the line Hamiltonian has the form of Laplacian plus potential, where the dimension can be arbitrarily high, D dimension, where D is 3 eta, depending on how many particles you are. But the form is this. Why do I say it's unbounded Hamiltonian? Is because from L2 to L2, again, a differential operator Laplacian is not going to be bounded because you are not L2 functions do not necessarily have bounded derivative. So you may argue with me. You can be like, D really does not make sense because even on classical computers, we never directly simulate unbounded operators. We always discretize them, and then they become finite dimensions, so what's the big deal? If you try to do that, this is a simple illustration. You can use other type of discretization, higher dimension. The story is the same. The point is that the size of the Hilbert space is n. And the number of qubits you need is polylog, little n. And so if you design your circuit carefully, your circuits, the gates per Curie is going to be poly little n. However, how many times you need to run the circuit, the Curie complexity, all of a sudden give you polynomial in n due to the operator norm dependence. So recall, getting polylog n is really we are hoping for from the quantum power of quantum computing for this particular problem. So poly n is not what we are going to set with. So just to mention a little bit more, one more is that typically, classically, we may not necessarily take this problem so seriously because, for example, if your classical simulation has a cost of n squared and the operator norm will give you another n to the 1/3, maybe you will say, okay, that's fine. So on the other hand, if your quantum algorithm is polylog n squared and then you have n 1/3, you will be, okay, no, that's definitely not fine, right? So that's the point. You may wonder, okay, then why don't I use the time-independent Hamiltonian simulation algorithm? Previously, I showed you there's this Trotter type and all different fancy version of post-Trotter type. The point is that if you try to do that, although this is indeed a time-independent simulation problem, but if you look at the operator norm after discretization, all of them acting on poly n. Even the commutator is not going to help you. There are some consolations, but they are not sufficient. So then the question is, how can we get polylog n for this type of unbounded Hamiltonian simulation problem? That's really what I'm going to talk about for the first part. This is the main question. All right. So the naive idea, the idea is very simple. So first of all, we are going to convert the time-independent problem into a time-dependent one by moving into the interaction picture. You may wonder, why do I want to do that? Well, first of all, interaction picture is just say these two are equivalent. For people who are not expert in this, it's just integrating vector methods if you'd like. So why do we want to, from time-independent to time-dependent, it seems that I'm turning the problem into something that is more complicated. Why do I want to do that? It turns out it's really good if we only focus on the operator norm dependence because we get rid of the A, which has the larger norm, say is the unbounded part. The whole thing only dependent on B, which is much smaller. But then you may wonder, what does the additional challenge? Is there any additional challenge? There shouldn't be any free lunch. So the additional challenge is really that now I'm treating the operator norm is large into the derivative is large. I'm treating the first source of oscillation to the second source. In particular, the derivative for this problem actually is poly n. So you really need an algorithm, a circuit implementation, so that when you implement the circuit, you are not reintroduce a poly n dependence. That's really what circuits need to handle. And you can imagine this is not a straightforward task, so to speak. So there are a number of works addressing related problems. I just want to say that from our one of our line of my previous results, we have been looking at this quantum Magnus algorithms. What we can show is that there is a very nice circuit construction in the sense that the circuit gates per Curie, if you'd like, or how many times I need to run these quantum circuits, only get away with log dependence of the derivative. So in our language, it's log dependence on n. So polylog n is really what I was hoping for. So all that I need to show is that the number of reputations that I need for this problem, in other words, how many time steps is independent of capital letter n, and then the whole cost, the number of repetition is independent of n. Each of the costs I get n, log n, so the overall cost will remain as a log scaling of n. So another nice feature that I'm not going to talk about today is actually these two works that the circuit that we constructed actually has an additional nice feature of the commutator scaling, which I showed you previously. Commutator scaling can do you wonders. So our algorithm is actually the only time-dependent general Hamiltonian where you can still return the commutator scaling and you can actually get both. This is the first time in literature. Well, that's a separate story for a separate day. So here I'm just going to show you, I'm not going to explain what they are, but just to say that this circuit give you a polylog n number of gate counts. You count how many gates there are, it's polylog n. So all that I need from now on is that, so this part has something to do with my circuit construction, and we can choose M as large as we like, such that these two error bounds get balanced. The size is the same. Because due to our circuit construction, we only pay a log dependence of the cost. But so this part is going to be at the same size of the first part. So from now on, I'm just going to focus on the numerical analysis of how many time repetitions I need to run the circuits. I'm saying that the circuits we can get away with polylog n, and I'm not showing you why that is, but we can. Is there a question? Please.
For the second quantity, where is the S? You take maximum over S, and we're.
Oh yeah, S is a time step. This here I'm looking at. You are right. There shouldn't be any S. This should be the derivative of t acting on the derivative of h, time derivative of h of s, where s is. But AB there shouldn't be any S. You are right. Thank you. Yeah, I corrected my slides from a previous. Thank you, it's a typo. All right, so from now on, we just need to focus this h squared, where h is the size of the time step size. H squared global convergence will means it's a second order algorithm, fine. Then all I need is to show the pre-error constant is independent of n. If that's the case, then the number of time steps I need, so the whole thing is bounded by certain precision, the number of time steps I need is independent of n. I just want to give everyone 3 seconds to convince yourself this is trivial. So what I'm saying is that I'm in this interaction picture where A is Laplacian or discretized Laplacian, which is associated with poly n that's large. I want to get rid of it. But if I have this, it's trivial to show, oh, I already showed you the answer. Oh, it's trivial to show that this only depends on B. 1, 2, 3 seconds. So it's certainly trivial to show because each of it is bounded by B and you just commute it a few times, it's B squared. So what one immediately will get is a second order algorithm with n independent error constant. In other words, we have a second order quantum algorithm with polylog n cost. That's what we want. Polylog n is really important here. So here is some numerics. I forgot to mention that previously I'm not going to go back. So previously, although if we run a time-independent simulation, we will not get an independent cost in the worst-case scenario. However, we can quantify a set of initial conditions or a set of observables where restricted to those specific error, and then you can vastly improve the estimate. So this is showing the worst-case scenario for the totalization. Well, it's no longer going up because unitary, difference between two unitary is upper bounded by 2. However, if you have good initial condition or good observable to start with, a class of observable, not arbitrary, and then you can get somewhere down to here. This was one of my previous work. But you look at our new algorithm, no matter the worst case scenario or the specific scenario you measure, it's way down below. So it's just showing that numerics is working. But so far, it's fine. It's not super excited. It's something that is working. It's the quantum circuits part is excited, but where's the mathematical analysis? So what we then plot is that, okay, then I'm going to look at how is the convergence in time. It's a second order algorithm, so I just plotted, I should see second order convergence. You plot that, You see that's not the case. You see fourth order convergence. By the way, if you run a spin system simulation, it will give you second order. However, if you run Laplacian plus potential, turns out it shows fourth order, although your algorithm is actually second order. Spin system gave you second order. It means that the second order is actually the right matching the lower bound. So what is going on? So at the very beginning, I thought, okay, sure, I understand what's going on. I'm sure I can figure this out. It's just because I have a commutator. Commutator can give me additional cancellation. Just imagine if I write my the time-dependent Hamiltonian in the Taylor expansion form. I just plug it in. A bunch of leading terms just canceled, so I easily get a additional order of h. From a second order, I get a third order. So that must be it, right? On top of that, actually, this will only give you third order. It turns out on top of that, if you go back to the original error estimate, there are 11 terms. You do a more careful analysis, you can actually get a fourth order instead of second. So we get a fourth order. Fine. But what's missing here? What you realize is that in the side of this argument, what you will reintroduce if you really use Taylor expansion is the derivative dependence in a polynomial fashion. In other words, if the derivative dependence is really, if the h itself is not oscillating, the derivative dependence is of order 1, of course you get fourth order, you have a fourth order convergence if you like. However, in our case, the derivative is not small at all. It operates on the poly n size. So if you look at this whole thing, something is off. So I was just trying to say that suppose, if this Taylor expansion argument really works, the error preconstant will depend on h. In other words, it will depend polynomially in n. So you will get an algorithm that is poly n instead of poly log n. That's really what we do not want. But then I was like, okay, but maybe this is the case. I have a fourth order convergence, and the constant is not uniform in n. Maybe if that's the case, I will just swallow it. But then what I plotted for different values of n, what you see is that everything is uniform in n. So that previous argument certainly is not going to work for this case. So despite the derivative is of order n, they are not small. Nevertheless, you can get uniform in n fourth order convergence. This is what we so-called superconvergence behavior, which means your algorithm in a certain scenario dramatically outperforms what is expected in general. It's a general term in numerical analysis. Then I look at this plot, everything is uniform. That's what I want to show later. But I then further ask myself, here I design an algorithm that is a quantum Magnus algorithm. What about classical Magnus algorithm? Maybe, Magnus is doing wonders, and all of the classical Magnus algorithm is also uniform. And then what I plot, and then you see they're not uniform, actually. So there is something uniquely going on with our algorithm, the quantum Magnus algorithm, that is making these wonders. So now I want to discuss a little bit about the analysis. So I go back to the original picture. I was like, I must be missing something in the error bounds. There are 11 different terms we need to estimate, and I'm taking the first two just for demonstration. You can easily estimate in a similar manner for the others. I was like, okay, if I can Taylor expand it, then you will realize all the t cubed term canceled. You get a fourth order superconvergence. By the way, you immediately get these are bounded by t squared. That's why you should have a second order, no matter what. But actually, that's not helping us, because recall A is unbounded operator. It's really in the poly n. And if you use the Taylor series expansion, you do not get a t squared. Instead, you have this remainder term. You can easily do a numerical just demonstration to show that the higher order term easily blow up in n. They are not supposed to be uniform. This is just to show that Taylor expansion is very tempting idea, but it's just a no-go. You couldn't get anywhere with this. So then what do we do? So this is the theorem that we were able to show. I first showed this theorem in the IPAM working group together with these two students on the continuous space cases. We also construct the corresponding quantum circuits and so on and so forth for the quantum Magnus algorithm. But what I'm going to present to you today is this discrete setting. So it states that I can look at this new commutator where I have h squared, so the second order becomes fourth order convergence. And all of the constant with finite n, I can show that all of the constant is actually uniform in n. And you can see there is a sort of additional condition that is acting on this size of H. But I want to emphasize this is actually not an additional condition. Because if previous Taylor expansion work, it means that H needs to be small. H needs to be smaller than the operator norm, which is poly n. However, I'm looking at the H is much larger. I'm looking at the opposite regime of Taylor expansion. In other words, this is really the regime. We want to say that the time step can be made independent of n. So this is the D regime that we want to look at. So this is really not an additional assumption. And the analysis that we use turns out to be some discrete microlocal analysis, and together with a two-scale symbol parameter. I will just show you some ideas very soon. So this is again numerical evidence just to show that it should be uniform. The previous error bounds should hold, but this is certainly not a proof. Now I'm going to discuss a little bit about high-level idea on what is the mathematical analysis we use to prove it. So I'm not going to look at two layers of nested commutators. I'm just going to look at one commutator. And from here, I want to show I have an S coming out with all of the pre-constant independent of the system size n. So from now on, I'm going to work with a potential that is bounded together with its derivative. So the potential spatial derivative, first spatial derivative, I'm going to assume is bounded. All right. So again, just to observe, you can use Taylor expansion, but then it shouldn't work because Taylor expansion requires your time step needs to be tiny, as small as 1 over n, or polynomial of 1 over n. So what I decided to use in the end is the semiclassical analysis. That's what I'm familiar with. So I'm going to use this Weil quantization. Specifically, if you are familiar with semiclassical Weil quantization, this is a semiclassical parameter equal to 1. Or you can also take the semiclassical parameter equal to S, and you can derive the similar results. So what is this Weil quantization? It just states that if you have position operator, you have multiplication, you have momentum operator, you have the derivative. It's consistent with our physical quantization. The point is that if we look at this, all of the previous issue is we want to perform some certain series expansion, say Taylor series, BCH formula, or Jensen-House formula. You try them all of them will require some smallness of the small time step S. But here, turns out I can rewrite this whole thing as a pseudo-differential operator, Weil quantization of this specific operator, and it is exact. There's no series truncation going on here, so throughout this procedure, I'm not requiring the size of S has to be smaller than the operator norm. And then what happens? You just plug it back in. Here, V is a potential acting only on X, so correspondingly, there are two pseudo-differential operators of these two specific form. If you have any background in semiclassical, you realize that the D bracket has a very natural analogy with the boson bracket. Specifically, you should have op of the boson bracket. What does boson bracket do? It takes a bunch of X derivative, a bunch of P derivative, but X acting on here, P acting on here. So because of the chain rule, you get an S coming out. So that's where I want to prove I'm gaining some time step S. And if the derivative is bounded, you can show all of these are actually just bounded. So you can actually do an explicit calculation, or you can also do a semiclassical calculation. You can also take the semiclassical parameter S, and then you will have X minus P, and then everything will work. There are a number of different ways you can make this rigorous. But that's not the result that I showed you. This is everything spatially continuous. The result that I showed you earlier are everything is spatially discrete. Nevertheless, I claim that it is uniform in n for finite number of n. Here, what I showed essentially, even after we make everything rigorous, is that the continuum limit is not blowing up. But I'm not showing any finite n the norm is uniform. Then the question is, what should we do? I will just discuss the challenge here, and I think then maybe depending on the time, maybe I will move on to the next topic. So what is the challenge? The challenge previously, if you realize, the whole argument really relies on this exact Golov theorem, if you like, where you are not making any errors. That's the crucial thing that makes this hold. However, if we have discretization, it turns out we will no longer, the reason this is exact is because the symbol here is p squared. It's a quadratic symbol, that's why everything is exact. However, after the discretization, we no longer have a quadratic symbol. We have approximation of a quadratic symbol. So the Golov theorem will not hold exactly. But then you may wonder, okay, then we have approximate version of a Golov theorem that could hold. I will address it very soon. But the first question before that is that now everything is going to be some discrete matrices. how do I work with these discrete matrices? You can certainly just multiply them out and so on and so forth. But we know that the differential operators, all the corresponding symbols, are really easy to work with. We have all of these PDE tools that we are familiar with. Is there a way to convert these matrices into the discrete, into these continuous symbols? Then all of the commutators are easy to calculate. All the Golov theorem I just can use. So the first thing we realize is that we can really identify this discrete matrix into a well quantization on the quantized torus, and this is exact, where the semiclassical parameter is chosen as 1 over the dimension of n. You can make this rigorous. And the point is that now I have some continuous phase space function. I can do the discrete microlocal symbol, microlocal well quantization, where I will have the matrices, which I argue are harder to work with because there are many components you need to analyze, versus you just do the regular quantization. You have a bunch of continuous operators, those who are really easy to work with. So what one can prove is that the spectral norm of these matrices bounds can actually be upper bounded by the L2 norm of the corresponding operators. What this essentially means is that we can use the PDE tools in the semiclassical microlocal analysis to deal with these discrete problems. So this is the very first step. We have a fully discrete problem, but nevertheless, I can use continuous PDE to deal with it because of this theorem. The second thing is that, well, then, okay, I do not have exact Golov theorem, but a Golov theorem has a very nice, approximate version of it. However, it turns out this is a bigger challenge beyond just use some discrete microlocal tool. The point is that a Golov theorem will not directly apply here. The reason is because the Golov theorem will hold only up to the so-called Ehrenfest time, which is log dependence on this parameter. In other words, in our case, is log n. However, if you look at this matrix time evolved conjugated by 2 unitary, the time scaling we need to look at is n squared, which is way longer than log n. That's what a Golov theorem is supposed to hold. So just playing around with this should definitely not work. That's why I was stuck for a few years that I have no idea what to do afterwards. So, but then it turns out there was a way we can reformulate this problem into a 2-parameter symbol class where this where we can work with the symbol calculus in this particular annals paper, and we can carry out the whole proof. There were some I'm not going to show you due to the time. You are welcome to talk with me afterwards. So I will just say that what we did is that using this discrete microlocal analysis plus 2 symbol parameter, we were going in the opposite direction of the Taylor expansion. And what makes me particularly excited about this application is that usually, semiclassical analysis is very helpful when your problem is in the semiclassical regime. There is a small parameter you are dealing with at the very beginning. However, recall in my problem, there's no semiclassical. It's not in semiclassical regime. I define myself the semiclassical parameter by the time step, by the spatial step, and it turns out to be a semiclassical analysis problem that we can deal with. That's the exciting part of this project. And the next, for the next the part, I'm going to talk about how to estimate an open quantum system with the idea of hypocoercivity. And I know there are many experts on this topic in the audience. I will just show you what can be done. Very briefly, just what is Lindbladian? Well, there are 2 formulations. Either you can work with the Heisenberg picture or the Schrödinger picture. They are equivalent, and the regular Hilbert-Schmitz normalize the inner product and so on. I'm not going to discuss about that. So my focus for today is the so-called mixing time. In other words, you have a closed quantum system interacting with the environment. I want to talk about how long does it take for it to thermalize. I know, okay, open quantum system under certain conditions is going to thermalize. How long does it thermalize? You may wonder, why do we care about this problem? Especially I'm talking about quantum computing. It turns out estimating mixing time is a crucial important problem for quantum computing purposes. There are people doing this business for various different problems. So the point is that the Lindbladian system, first of all, you can show it actually can do universal quantum computation. There are various applications, but I'm not going to go through the list. The point is, in many cases, you can reformulate, say, your classical optimization problems or your ground state problem into finding a solution. You formulate it as the solution of the equilibrium of your Lindbladian equation. Then the crucial question, whether there is a quantum advantage or not, is how long does it need? You cannot take t to infinity. You are truncating somewhere to simulate it. So the question really is, how long is the mixing time? Is the mixing time polynomial in little n? From now on, I'm using little n is the number of qubits, number of the system size. Is it poly little n or exponential in n? That will make a crucial difference. If it's exponential in n, then it's not quantumly efficient. If it's poly n, then it's quantumly efficient. I know I'm running out of time. Just here, the previous, there are various different, this is a really celebrated field. There are various different techniques, the state of art to estimate mixing time. The idea is really that you need to start with a Hamiltonian. You pick your favorite inner product, GH, GNS, KMS, whichever, or any interpolation in between. You take your Lindbladian is detail balance from the very beginning. And then you estimate the lower bound of the spectral gap. You have a gap estimation. And then you get a decay in the Heisenberg picture. You can use duality into to get a mixing time of the state picture. That's typically the idea. In particular, if you have a gap that is 1 over poly n, correspondingly the mixing time will be poly n. So this means quantumly efficient. And on top of that, you can actually further tighten the bound. For example, if G is lower bounded by just a constant, you can use log sorptive inequality to better it a poly log n, which is poly log of the size of the Hilbert space. But the existing work takeaway is really that we need to estimate the spectral gap of the Lindbladian. And the first starting point is always you need to check you have a Hamiltonian, Lindbladian that is detail balance in certain inner product. But the question is certainly that, in many of the cases, because we have a Hamiltonian and the Lindbladian term adding together, in many of the cases, Hamiltonian itself can be very simple. Say you have transverse field Ising model where you know everything. And the dissipative part, which is the jump operator, may also be very simple. Suppose you have dephasing noise of some poly noise where pretty much you can explicitly calculate everything. However, as soon as you add them together, all of a sudden it's become a much more difficult problem compared to before. So our question is really that can we sort of utilize these two parts of information somewhat separately, and maybe results requiring the whole Lindbladian needs to be detail balanced, but still yield some mixing time estimates. That's the question that I want to, that's the question of this part. I don't think I have enough time to tell you what we did, but the high level message is that yes, we can propose a theoretical work where we can propose a set of conditions on H and D sort of separately, and the whole Lindbladian do not need to satisfy detail. I'm not saying any non-detail balance Lindbladian I can deal with it. I'm just saying there are specific cases where I can deal with it. And then the question is, you have a nice mathematical framework. Is there any applications? If there's no applications, you prove amazing properties, then it's great, but it's less applicable. So there were a number of in the Lindbladian system where previously this system there does not exist any previous techniques can analyze them, and we can analyze them using this particular framework. And the idea of proving it is really a generalization of hypocoercivity, which is coming from the kinetic theory. So how much time do I have? Maybe 5-ish minutes, 3. Oh, okay. So, okay, maybe I do not have. Okay, just to say that hypocoercivity is a very important concept, which was, I believe, coined by so there are many significant works. I will just say what I like the most two frameworks. One is by Debol, Mohan, and Schmeisser. Francois also mentioned it this morning. The other is by Arnold and Eric Carlin. I do not think I have the idea have the time to talk about. This is actually a very simple ODE example taken from Arnold's talk where I attended back in 2017. But I do not think I have the time to go through with you this ingenious example he constructed to demonstrate what is the meaning of a hypocoercivity. So I just will mention our result, and then I will end. So you can pick your favorite inner product, particularly pick J and H. You can pick any other interpolation of alpha. And then we can look at the difference, because this is a linear equation. We just look at the difference. So there are, So maybe let me just still mention this, I think. So the intuition is that, let's imagine I'm going to decompose my observable A, my operator A, into two parts. One part lives inside of the kernel of H, of D. The other part is outside of the kernel. So by the dissipative nature of D, so hopefully, anything that is outside of its kernel get damped because D is a dissipative operator. You look at what is left over, which is inside of the kernel, and suppose your Hamiltonian has certain property. In particular, if it's 38 outside of the kernel, then it will be damped by the next time step. So this is how you can treat the system sort of separately. Nevertheless, globally, you will get a global convergence results. So this is sort of the idea where the globally D is dissipative, and each of the Hamiltonian is going to stir it outside, so it's got dissipative next time. This is just intuition. This is not how you prove it. You should construct the Lyapunov functional to prove it. So there are just due to the time consideration, I will not discuss about the details of the conditions. This is just say, okay, there's dissipative nature. This is also corresponding to hypocoercivity. And then the Hamiltonian needs to stir outside of the system. And then this constant Cm is associated with the system size, typically in a polynomial in n fashion. And I will just say that the mean theorem is that under this framework, the whole Hamiltonian do not need to be detail balanced. And nevertheless, we can show that there is a quantitative mixing time estimate that we can calculate. In particular, you can imagine we are interested in showing if this is poly n, small n, then it means quantumly efficient. Otherwise, it's not quantumly efficient. So there are a number of examples that we can quantify just to say defacing noise, transverse Ising model, Heisenberg model, and the quantum work, and so on. I'm running out of time, but all of those I can prove it. There are poly n. So this part is just some applications. I'm ready to summarize. So today I talk about two things. One is a closed quantum system unbounded Hamiltonian simulation, where I hope I justify to you that although it's not in the semiclassical regime, but semiclassical microlocal analysis can do you wonders, leading to the superconvergence result. In the open quantum system, I hope I demonstrate to you that hypocoercivity can indeed be used. So the open question would be, can we generalize other hypocoercivity? There are various different hypocoercivity framework. Here we are just taking a look at a particular one of them. And also, I believe this discrete microlocal plus two-scale symbol analysis can be applied to more general numerical analysis problem that is not necessary in the context of a Hamiltonian simulation. I would be interested in looking at all of these future directions. With that, thank you for your attention.